In this video lesson, we're going to start to explore transformations of functions. Our objectives through this lesson are to look at the algebraic parameters that define a transformation of a function, to identify different types of transformations, and ultimately to look at the impact a transformation has on points and the overall sketch of a function. In looking at transformations of functions, we're going to explore the three types: dilations, translations, and reflections. And it's important to know that these three types of transformations can impact a function both vertically and horizontally. And in this video, we're going to explore the vertical translations exclusively. So let's look at each of those types of transformations to define exactly what they are. We'll start with a dilation. A dilation is an expansion or a contraction of a function. We often refer to them as stretches or compressions. And what this means is it's a transformation that adjusts the shape of a function and its size, but not affecting its position or orientation. Our second type of transformation is called a translation, or sometimes referred to as a shift. And basically this is a change in the position of a function. So it doesn't change its shape, but it will alter its location, moving it up, down, left, right, or some combination of those. And then finally we have reflections, which are not a change in the shape of a function or technically its position, but rather a change in the orientation of a function. So flipping it vertically or horizontally or both. So this video is going to focus only on vertical transformations. We will begin with vertical dilations and then talk about reflections and translations after that. So to begin, let's consider three functions. We'll start off with our base function, f of x equals x cubed. And then we'll define two more functions based on this function. We'll say that g of x is equal to 2 times f of x, and h of x is equal to 1/2 f of x. Now I've defined g and h in terms of f, because that's how transformations are applied. The idea is you're taking one function and transforming it into another function. But in order to explore this concretely, we're going to want to actually know what the equations for those functions are. So if I sub in f of x into g of x, instead of having 2 times f of x, I'll now have 2 times x cubed. And likewise for h of x, instead of having 1/2 f of x, I will have 1/2 x cubed. So now I have equations for both g and h in terms of f. With all three equations of these functions now, we can start to look at a mapping for how it's going to take some x values and map them to y values. So I'll start by looking at just a few sample x values for f of x. So I've used -2, -1, 0, 1, and 2 as my x values, and by inputting them into the function, I get that they map to the y values -8, -1, 0, 1, and 8. And so this is going to give me just a few starting points to play around with to understand how these transformations work. And so what we'll want to do next is the same thing for g of x and h of x. So I have here the values for g of x. Again, using the same x values, I'm looking to see what they map to under that new equation. And I get the values -16, -2, 0, 2, and 16. And now I'll repeat that process for h of x. So I see that -2, -1, 0, 1, and 2 are going to map to -4, -1/2, 0, 1/2, and 4. So all of these y values are simply found by substituting those x values into the equation and evaluating. So now it's important for us to look at these three mappings and try to establish what it is that changed between them. How did they differ because we multiplied by a 2 or multiplied by a 1/2? And if you look at the x values, there's of course no difference because we use the same x values for each function. But if we look at our y values, there's a connection between them as we look from f to g to h. So if I look at my default values for f, if I move then over to g, I see that it's just all my y values for f, but having been doubled. And if I compare f and h, I see the values have actually all been halved, which is appropriate because that's the value I multiplied by when I transformed the function, right? G of x was 2 times f of x, so all its y values were 2 times bigger. And likewise, h of x was half of f of x, and all of its y values were half the size. So what we're witnessing here is the effect of that vertical dilation. Essentially, if you have functions f of x and then a function g of x that's defined as a times f of x, then we can describe the transformation that occurs as follows. If the magnitude of a is bigger than 1, then we would describe the transformation as a vertical stretch. And so in this line, you may see some notation you're not familiar with, and it's the vertical bars around the A. Whenever we put vertical bars around a number, what we're saying is we're looking at what's called the absolute value of a number, or just its magnitude. So we don't concern ourselves with whether it's positive or negative. The idea is if the magnitude of the number, the size of it, is bigger than 1. So for example, 5 has an absolute value greater than 1, but so does, say, negative 10. So all of these values have a magnitude bigger than 1. And any a value like that is going to result in a vertical stretch. Another way of thinking of the graphical impact of a vertical stretch is to think that the y values have all moved further from the x-axis, which means they've either moved further upward away from it or further downward if they were already below the x-axis. So the other thing we saw with h of x is if the magnitude of that a value multiplied in front of a function, if it was less than 1, essentially meaning that it falls between negative 1 and 1, so it's a very tiny number, then the transformation we have is a vertical compression. Another way of thinking about a vertical compression is that your y values have moved closer toward the x-axis, meaning that if they were above the x-axis, they've moved downward, they've been compressed towards it, and if they were below the x-axis, they've moved upward a bit, they've been compressed again towards the x-axis from below. And so here I've actually included a graph of the 3 functions that we looked at. The blue function is 2x cubed, the red one is just x cubed, and the green function is 1/2 x cubed. So hopefully you can see the effect of that stretching and compression. The red function in the middle is the starting function, so the blue function's been stretched further away, and the green function has been compressed towards the x-axis. And so our general rule in dealing with a vertical dilation, a stretch or a compression, we essentially recognize the idea that if g of x is a function that's taking function f of x and transforming it because we're multiplying a value of a out in front, then what it's going to do to the points is it's going to take all the points x, y on my original function, and it's going to map them to new points on g of x, where the x values don't change, but all the y values get multiplied by whatever that a value is. And so knowing this mapping is a really quick way to transform points. If you know the function has been multiplied by 5, for example, so we have instead of x squared, 5x squared, we know that we can generate the new points by just multiplying every y value by 5. Now, I talked about stretches and compressions only coming into play based on the magnitude of the a value, and I said that the negatives didn't really matter in dictating a stretch or compression. But that doesn't mean the negatives don't matter at all. In fact, negatives are very important to dictating something about the function, and that is its orientation. So if the a value is negative, what we actually have potentially in addition to a stretch or a compression would be a vertical reflection. And what that's going to do is it's going to reflect the function across the x-axis. So picture the x-axis as being a mirror for the function, and the function is going to be mirrored across it. Any points below will be mirrored to above the x-axis. Any points above will be mirrored to below the x-axis. We can see why this occurs if we extend our mapping idea from stretches and compressions, right? If the a value is negative, and when we apply this transformation, we multiply every y value by a, essentially what it's going to do is make any positive y value negative, so jumping from above the x-axis to below, and likewise a negative y value, when multiplied by a negative number, will become positive, and that's going to move it above the x-axis. So this is really just an extension of our idea of vertical dilations. Reflection kind of piggybacks on that same rule. And so now we're going to look at some vertical translations. So I've given you 3 functions again. We have f of x is equal to x cubed, and then g of x is going to be equal to f of x plus 1, and h of x is f of x minus 1. And so like with our vertical dilations, even though transformations are defined based on some initial function, I'm still going to want to see what the equations are for g of x and h of x. So we're going to start by substituting in f of x into the notation here for g of x and h. So when we substitute in f of x to the notation we have there for g of x, instead of having g of x equals f of x plus 1, we now have g of x equals x cubed plus 1. And then likewise for h of x, instead of having f of x minus 1, we'll have x cubed minus 1. And so from here, I'll repeat the process we used when we looked at dilations. So we'll start off with a mapping just for the regular values of f of x. These are the same ones we looked at before. So no need to even recalculate these. You already have them written down. But let's then calculate what values we get for g of x and h of x when we plug -2, -1, 0, 1, and 2 in as inputs for those functions. So when I calculate the values here with g of x, I get that -2 maps to -7. With -1, I get 0. With 0, I get 1. With 1, I get 2. And with 2, I end up with 9. If I do similar calculations for h of x, -2 I see maps to -9. -1 maps to -2. 0 is going to map to -1. 1 is going to map to 0. And when I look at what 2 maps to, I'm going to get 7. So now if I take a moment to look at how these values are related, we should be able to spot sort of a pattern in how these y values are connected. So if I look at the y values for f of x and then compare them to g of x, what I see is that the y values in g of x are all 1 more than their counterpart in f of x, which again makes sense because g of x was just taking f of x and adding 1 to it. So essentially all it's done is it's increased each y value by 1. And likewise, when I look at h of x, I should be able to notice that those y values are all 1 less than what I have for f of x. And again, that makes sense because the transformation that I applied, the equation for h of x, was simply taking f of x and reducing it by 1. So each y value is 1 less than it was originally. So what we're seeing here is the numerical evidence of that vertical translation, a shift up or down. And so if we were to generalize, what we're going to say is if we have a function f of x, and then we have g of x, which is defined as f of x plus some number d. And d could be positive or it could be negative, but we're adding some constant on at the end. Then the way we're going to describe our translations is this. If d is greater than 0, then the transformation is a vertical translation upward, or a shift upward. So if I were to have f of x plus 3, that's the result of a shift 3 units up for the entirety of the graph. So a positive d value means the y values are increasing and shifting the whole function upwards on the graph. And so the complementary idea to that, which we saw with our x cubed minus 1, is if d is a negative number, we're going to see the opposite effect. The transformation will be a vertical translation downward. This means that all of our y values will decrease. So we saw with f of x minus 1, they all decreased by 1, and graphically that's going to move it downwards. The bigger the decrease, the further it shifts down. And so to examine this graphically, here again are the graphs of those 3 functions. So we have x cubed, which is the red function in the middle, and then we have x cubed plus 1, that's the blue function that was shifted upward, and x cubed minus 1, which is the green function that's shifted downward here. And so again, if we're just to consider a generalized mapping, where g of x is taking some function f of x and adding a value d to it, then what we're going to notice is that all of our points on f, which we'll call just regular points x, y, they're all going to be mapped to new points where the x value doesn't change, but the y value has d added to it. And the reason why I just say d added to it is because, again, if d is positive, we're going to see an increase in those values. But if d is negative, by adding a negative number, we're subtracting, we're reducing those values. And so this is a generalized way to look at those transformations and the vertical shift up or down that it's going to have. So that's a discussion of vertical transformations. We've looked at vertical dilations, vertical reflections, and vertical translations. And so with that information, you should be able to start to play around with understanding what transformations are happening, what impact it has on the function, even determining the equation of a function that has undergone transformations. And so once we have discussed horizontal transformations, which will be next class, we'll be able to tie it all together and look at the impact it has on sketching a function. And so we'll do some sketching activities where we apply different transformations and see what happens. And so your main practice now is going to be to make sure you understand how to take an equation and apply a transformation algebraically and have that same impact show up relative to the different points you might be discussing. It's also going to be very important now that you can identify transformations, so know when something has been vertically stretched or shifted or reflected, which means you should be able to match an equation up to a graph if you were given one.